The experiment I'm proposing is the kinetics of the iodination of cyclohexanone. A little bit of theory and background to start off. Many reactions occur through a series of more simple steps. These simple reactions are called elementary reactions, and the collection of these more simpler reactions makes up the mechanism of the whole reaction. There can be different proposed mechanisms for any given reaction, but the valid mechanism must agree with the kinetics of the reaction. The reaction I'm proposing to study is the halogenation of a ketone. You start off with ketone and then you add diatomic halogen, and you'll get basically your ketone with the hydrogen removed, except your halogen will be added where the hydrogen was. But I'm proposing we do this with cyclohexanone, which is a cyclohexane ketone, and iodine. So then we'll get this ketone over here with the iodine there, and some equations that I propose that we would use would be this equation here. A rate law can be written as such, where the change in concentration is equal to the rate constant times the concentration of each of the reactants to a particular power that needs to be solved for. More equations that we will be using in this experiment would include Beer's law, where A is the absorbance, C is the concentration. This E is the molar absorptivity of the substance, which depends on the specific substance in question and the wavelength that you'll be working at. L is the path length the light travels through the sample. We can solve for the path length and the molar absorptivity by analyzing a known concentration sample, and once we get the absorbance of that, we can solve for the path length and the molar absorptivity. The relationship between changing absorbance and changing concentration can be written as this equation down here, which says that the negative value of the change in absorbance over the change in time is equal to the negative value of the molar absorptivity times the path length times the change in concentration over the change in time. Some chemicals we'll need to perform this reaction include cyclohexanone, hydrochloric acid, deionized water, and potassium triiodide. This table here shows the volume of each stock solution we'll need to add for each of the trials we're going to run. Some materials we'll need to perform this reaction include a hot water bath, glassware to prepare some solutions, an Erlenmeyer flask to perform the reaction in, a UV vis spectrophotometer to measure the absorbance of the solutions, and some cuvettes to use in that UV vis spectrophotometer. How we're going to actually perform this reaction is we're going to turn on the hot water bath as soon as we get into the lab to ensure it's up to temperature when we're ready to use it. And then we're going to combine the hydrochloric acid, the cyclohexanone, and water in the Erlenmeyer flask, and we're going to place that flask and a separate flask of the potassium triiodide in the water bath, which should be about 30 degrees Celsius, and we're going to let them equilibrate for about 15 minutes until everything's up to temperature. Once we've waited about 15 minutes for the solutions to thermally equilibrate with the water in the hot water bath, we're going to add some potassium triiodide to our reaction flask, which contains the hydrochloric acid, the deionized water, and the cyclohexanone. And the amount we're going to add is stated in table 1 I showed earlier, and that'll change for each trial we run. After we add this portion of potassium triiodide, we're going to immediately start a timer, and we're going to take a small portion of this reaction, of the reaction mixture, and we're going to analyze it at 565 nanometers. And then we're going to continue taking small portions and analyzing these small portions every 2 minutes for the next 20 minutes. We're going to then repeat this procedure with each of the trials, 1, 2, 3, and 4. And we're also going to have to analyze a portion of potassium triiodide of a known concentration, and then we're going to use that absorbance value to solve for the molar absorptivity and the path length that we're going to need to use to perform more calculations later. After we've completed all the reactions for each trial and got all our data points, each data point being the absorbance every 2 minutes for 20 minutes, We can graph this absorbance as a function of time, and then from this graph, the value of that'll be the slope of the trend line of this graph will be the change in absorbance over change in time, which we can then use Beer's law to determine the change in concentration of triiodide over the change in time, and that'll be equal to our rate law, which we're trying to find, and the concentration of the cyclohexanone to a specific power that we need to solve for, the triiodide concentration to a particular power that we need to solve for, and the hydrogen ion concentration to a specific power that we need to solve for. If we take two of these separate trials where the concentration was only varied for the initial concentration for each of the reactants was only varied, one of them was only varied, we can combine these two reactions and solve for A, B, and C. Combining these reactions and solving for A, I've shown down here. You can use a similar method to solve for B and C, and then the only thing we have left to solve for is the rate constant. Then we use the value we calculated for the molar absorptivity times the path length, the value of A, B, and C we've calculated, and then we're able to solve for the rate constant. And then we calculate the average value of the rate constant and its standard deviation, and we compare that to known literature values. And that's the experiment.